April 28, 1945, East China Sea. Dawn broke over a Japanese convoy moving cautiously through contested waters. Merchant ships and their escorts steamed in tight formation, carrying oil and supplies vital to a nation already cut off from most of its trade routes. Lookouts scanned the horizon and sky, but all appeared calm. Minutes later, the calm collapsed into chaos. Without warning, explosions tore into the convoy. A patrol vessel disintegrated under the force of a sudden blast. Nearby ships swerved violently, unsure where the attack came from. Anti-aircraft crews manned their guns but found no target. No aircraft dove from the clouds, no submarine wake cut the surface. To the men aboard those ships, it was as if destruction had struck from an empty sky. The source of this invisible assault was a revolutionary American weapon, the ASM-N-2 Bat missile. Carried high above by U.S. Navy PB-4Y, 2 privateer bombers, each Bat was a 1,880-pound glider with a 1,000-pound warhead and a radar eye in its nose. Once released, the Bat could search, lock onto a moving ship, and guide itself to impact entirely without human control. No radio operator steered it, no pilot corrected its course. It was the first fully autonomous, radar-guided missile ever used in combat. That morning, 2 of these weapons left their launch aircraft miles away and silently descended toward the Japanese formation. Inside their sealed noses, vacuum tube computers and servo motors continuously adjusted their flight path as S-band radar seekers hunted for the strongest ship reflections. By the time the Japanese escorts realized something was wrong, the missiles had already struck. Chaos and confusion followed, crews reported explosions from nowhere, and surviving ships scattered in panic. The April 28 attack was not unique. In the final months of World War II, similar strikes near Borneo, Okinawa, and the Chinese coast proved that human eyesight and courage no longer defined naval survival. The Bat missile allowed American forces to destroy ships beyond the range of anti-aircraft fire, adding a new dimension to the already overwhelming pressure from submarines and B-29 mining campaign. This was more than a tactical success. It marked the arrival of automated warfare, where machines could find and destroy targets on their own. By 1942, the Pacific War had evolved into a brutal contest of attrition across thousands of miles of sea. Japan depended on long, fragile supply routes to feed its cities and fuel its fleets, while American submarines and carrier strikes increasingly choked those lifelines. But attacking convoys was costly. Pilots had to dive through dense rings of anti-aircraft, fire, weather, and zigzagging, frequently spoiled, carefully planned runs, and torpedoes and bombs often failed to find their marks. Naval planners concluded that brute force alone would not suffice. What was needed was standoff precision, a weapon released from altitude that could seek and strike moving ships in poor visibility. Germany had tested radio-steered glide bombs, but their dependence on visual control and radio links limited range and left them vulnerable to jamming. The United States, therefore, sought a self-guiding device, one carrying its own sensors and guidance, capable of course corrections after release. In January 1942, the Navy issued such a requirement, a specification that pushed existing radar and analog electronics to their limits. Combining industrial scale, new long-range aircraft, and fast-moving electronics research, American laboratories, naval officers, and civilian engineers launched the secret program that produced the ASM-N-2 Bat. In January 1942, a terse Navy requirement for an air-launched, self-guiding weapon did not linger on paper long. It accelerated into an organized project under the National Bureau of Standards in Washington, D.C. Leadership fell to Dr. Hugh Dryden, an aeronautical engineer who treated the task less as weapons design and more as a problem in control systems. Dryden framed the challenge plainly. If a missile could sense its environment, compute corrections, and alter its flight surfaces autonomously, it could strike moving targets from a safe standoff distance. He recruited an unusually interdisciplinary team airframe aerodynamicists to design a stable glider, radar specialists from Bell Telephone Laboratories skilled in S-band circuitry, and physicists and electrical engineers from universities and government labs to compress sensing, decision-making, and actuation into a compact, rugged package. The list of required capabilities read like a catalog of technical firsts: an airborne radar capable of detecting a ship at tens of miles, an analog guidance system to translate radar returns into continuous steering commands, and servo mechanisms robust enough to survive carriage and release while making precise control inputs in flight. Each element strained the limits of 1940s technology. Vacuum tubes were the era's computing elements, but were fragile, heat-sensitive, and prone to failure in humid or shocky environments. Servos of the day were electromechanical and required careful mounting to resist the violent jolt at separation. The airframe itself had to balance conflicting demands, light and aerodynamic for a long glide, yet structurally strong enough to carry a 1,000-pound ASM-N-2 warhead and withstand the stresses of high-speed release. By mid-1943, prototypes were flying at Naval Air Station Patuxent River, and the early tests exposed predictable and surprising faults. Tropical humidity condensed inside the seeker housings and shortened vacuum tube circuits. Radar seekers sometimes locked onto coastal reflections or stationary land masses instead of a moving ship. Servo attachments broke under repeated launches. Each failure provided data. Engineers iterated rapidly, improved sealing techniques protected electronics from moisture, analog filter circuits were refined to discriminate moving targets from static clutter. Radar signal processing was adjusted to favor Doppler returns consistent with a vessel's motion. Servo mounts were strengthened and rethought. Importantly, the US approach differed from Germany's hand-steered glide bombs. Where the German programs relied on skilled operators guiding weapons by radio, the American program pursued industrial standardization, interchangeable parts, repeatable assembly lines, and engineering changes that could be pushed directly into production. By late 1944, the program had made the leap from laboratory experiment to production engineering. Manufacturing lines were established, quality control practices introduced, and some 3,000 Bat units were produced, of which roughly 420 were shipped to the Pacific Theater. Training squadrons learned to carry the heavy gliders under PB-4Y, 2 privateer patrol bombers, and to release them from altitudes that maximized glide range while keeping the launching aircraft beyond the worst of enemy defenses. The result of this concentrated effort was the ASM-N-2 Bat, a heavy glide bomb with a roughly 10-foot wingspan, a 1,000-pound warhead, and a nose-mounted S-band radar seeker. The Bat's internal architecture was deceptively simple in concept, yet fiendishly complex in execution. The seeker emitted radar pulses and scanned for the strongest moving reflection consistent with a ship-sized target. Its analog brain, built from vacuum tubes and relay logic, continuously compared the missile's heading to the target bearing and generated corrective signals that drove electromechanical servos. The weapon executed a closed-loop feedback cycle sense, compare, adjust dozens of times per second, guiding itself without any further input from the launching crew. In favorable conditions, open ocean, isolated targets, and moderate weather, the Bat could find and home on a vessel from miles away, a true fire and forget capability. Those same choices also imposed limits. Vacuum tubes could fail under tropical humidity, sea clutter, rain, or nearby land could mask or mislead the seeker, and the Bat proved most effective against isolated, slow, or stationary targets in open water rather than against fast or heavily clustered coastal convoys. Even so, the program proved a defining wartime synthesis. Laboratory science, control systems theory, and mass production fused into an operational weapon that, within 3 years of a hopeful Navy memo, delivered the first fully autonomous guided strikes in combat. From late April through mid-August 1945, the Bat missile was committed to combat in limited numbers. Operational deployment centered on long-range U.S. Navy patrol bombers, especially PB-4Y 2 privateers of Patrol Bombing Squadron 109, tasked to interdict Japanese shipping routes from the East China Sea to the approaches of Borneo and Okinawa. Approximately 420 missiles were shipped to the Pacific, and surviving records indicate that around 100 were launched on combat sortie. The first operational attempt occurred on 23 April 1945 during attacks on Balikpapan Harbor, Borneo. 2 missiles were released but failed to guide correctly because of electronic faults, illustrating how fragile early vacuum tube technology remained in tropical conditions. 5 days later, on 28 April, VPB-109 recorded the Bat's first confirmed success. A Japanese patrol vessel southeast of a convoy route in the East China Sea was struck and destroyed without the crew of the launch aircraft ever making visual contact. Success followed quickly. On 1 May 1945, a second small coastal craft was sunk, again near Borneo. The most significant engagement came on 28 May 1945, when a Bat homed in on the Japanese escort ship Kaibokan Oni near Okinawa. The missile struck squarely and left the ship so badly damaged that it never returned to full service, even though it did not sink. Another confirmed sinking occurred on 18 June 1945 when a small patrol vessel was destroyed. In addition, squadron logs credit Bat missiles with the destruction of at least one oil storage tank on land, demonstrating capability against fixed shore targets. Other squadrons, notably VPB-123 and VPB-124, launched missiles but did not record confirmed kills. Many sorties ended with missiles jettisoned or with seekers failing to lock onto targets in cluttered or coastal waters. Post-war analysis by the Joint Army-Navy Assessment Committee concluded that, of roughly 100 combat firings, 3 small vessels were sunk and 1 escort-class warship was heavily damaged. While these results might appear modest compared to the thousands of ships sunk by submarines or conventional bombing, they carried strategic weight. Japanese captains reported explosions from nowhere, and convoy movements slowed in areas where Bat-equipped squadrons might operate. The weapon's psychological effect far exceeded its tonnage destroyed. It demonstrated that autonomous, radar-guided strike was possible in combat, validating the concept and providing a foundation for the guided missiles that would dominate naval warfare in the decades to come. The operational record of the Bat revealed more than tactical innovation. It exposed a profound industrial and technological divide between the United States and Japan in the final year of the Pacific War. By 1945, the United States had mobilized an economy capable of building advanced electronics, precision airframes, and standardized components on an industrial scale. American factories produced radar sets, vacuum tubes, and servo mechanisms in the tens of thousands, with quality control that allowed parts to be interchangeable and rapidly upgraded. When early Bat deployments showed that tropical humidity damaged guidance tubes or that seekers occasionally locked onto islands, engineers quickly modified seals and circuitry and fed those improvements back into production lines without interrupting supply. Japan's industrial base was organized very differently. Warship equipment often relied on hand-fitted artisan assembly. Radar sets were few and prone to failure. Replacement parts were scarce because copper, high-grade steel, and fuel were in crisis-level shortage. Even when American radar equipment was captured, Japanese engineers often identified individual parts, but struggled to understand how those parts worked together as an integrated system. Developing an autonomous, radar-guided missile was far beyond their technical and manufacturing reach. This disparity reflected not only production capacity, but philosophy of war. The United States approached conflict as an engineering problem to be solved with machinery and science. The Bat's development, combining miniaturized radar, analog computing, and automated control, showed how American planners invested heavily in technology that reduced the need for human decision-making in combat. Japanese naval doctrine moved in the opposite direction. It emphasized close-range engagements and spiritual resolve, culminating in the kamikaze strategy, where the pilot became the weapon. While US squadrons released machines that guided themselves, Japanese forces relied on human sacrifice to offset shrinking resources. These two approaches, automation versus personal martyrdom, defined the war's closing months. The industrial contrast extended to the psychology of sailors. US crews trusted machines to do what was once a pilot's job, while Japanese crews confronted attacks they could neither detect nor counter. This imbalance foreshadowed post-war military trends. Future conflicts would be shaped less by individual courage and more by the capacity to design, build, and maintain complex technological systems at scale. Through this lens, the Bat's significance was never limited to the 3 small vessels it sank. Its real impact lay in demonstrating that an industrial democracy could transform emerging sciences, radar, control theory, and analog computing into operational weapons faster than an adversary rooted in older manufacturing and combat traditions. Although the Bat missile's confirmed combat record was small, 3 ships sunk, 1 warship crippled, and a few shore installations destroyed, its long-term impact on warfare was profound. In 1945, it proved that a weapon could find, decide, and strike without human control after launch, something no other nation had achieved. Every subsequent generation of precision weapons, from early post-war anti-ship missiles such as the US Harpoon and France's Exocet, to modern air-to-surface weapons like the Tomahawk cruise missile and JDAM smart bombs, traces a conceptual lineage back to the Bat's radar seeker and closed-loop guidance system. The program also left a strong industrial and scientific legacy. Engineers who worked on the Bat carried its lessons into the Cold War. Dr. Hugh Dryden went on to help create the US space program. Others shaped the design of later missiles, such as the Sidewinder. The experience taught American industry how to harden electronics for flight, miniaturize radar systems, and integrate sensing and control into compact, reliable packages, capabilities that would underpin not only weapons, but also civilian aviation and space exploration. At the same time, the Bat raised ethical and strategic questions that remain unsettled. By removing a human operator from the final decision to strike, it introduced a new category of combat where machines applied lethal force independently. Japanese sailors, who faced sudden destruction without warning or a visible attacker, experienced the first shock of a reality that later generations would recognize in drone strikes and autonomous weapons debates. Military ethicists now describe that moment as an early crossing of the line between human-directed combat and algorithmic warfare. Post-war evaluation by the Joint Army-Navy Assessment Committee called the Bat only moderately successful in tactical terms, citing its sensitivity to weather, electronic failures, and difficulty in cluttered coastal waters. Yet those assessments also acknowledged that proving the principle mattered more than the immediate results. The Bat demonstrated that automation could work in combat and that American industry could move an advanced weapon from concept to battlefield in barely 3 years. Seen from today's vantage point, the Bat missile was less a weapon of destruction than a proof of future conflict. It foreshadowed a world where radar seekers, digital processors, and autonomous guidance would define how wars are fought. Its a few wartime sinkings are long past, but the questions it raised about accountability when machines make life and death decisions, about the balance between human skill and technological force, remain active in every modern debate over armed drones and autonomous systems. The ASM-N-2 Bat did not decide the Pacific War. That victory came from the combined weight of submarines, carrier aviation, and strategic bombing. But in its brief service, the Bat marked the starting point of precision warfare, showing that the future of combat would depend not on larger fleets or greater courage, but on the capacity to create and control intelligent weapons. More than 70 years later, every missile that guides itself to a target carries a part of that legacy.